Hi everyone, hope you're keeping yourself safe and everyone's doing well. It's now time for our next lesson, which is going to be all about electricity distribution. So, in the previous lesson, last week, what you did, basically you did some research on how electricity is generated. So, it can be generated in a power station or a wind farm or kind of something similar to that. And then we transport it to our homes, and that's what we're going to be looking at today. How do we get that electricity from wherever we've generated it to our homes, to our businesses, anywhere that we're going to need the electricity to be? How do we get it from one place to another? So let's have a look at our learning intention. Learning intentions today to explore the challenges surrounding electricity distribution and to examine the solutions to these problems. And there's one solution in particular we're going to be concentrating on. Our success criteria: I can discuss the challenges that exist in transporting electricity. I can explain how a transformer can help overcome such challenges. I can perform calculations that predict the input or output voltage from a known transformer. It sounds like there's a lot there, don't worry, we'll go through it kind of step by step. We'll have a look at the challenges, the solutions, and then we'll introduce the calculation. Don't worry too much about the calculation, remember. At this kind of level, we will give you any equations that you need in the form that you need to. You don't need to worry about any rearrangement at this point in time. Okay, so how do we get electricity from wherever we've generated it to our home? Well, let's start off with where we generated it. So we generate it at the power station, at the wind farm, wherever we're generating it. You guys will no doubt have seen these devices about the place. These are pylons. Obviously, steer well clear of them. Very, very high voltage travelling along those power lines that are connected to the pylons. So they transport our electricity around the country, and then of course it gets to our homes, our businesses, or wherever we want it to be. A lot of people see this as being the kind of steps in the process. It's generated, it's transmitted, and it's there, and we've got it, and that's useful, and that's brilliant. If that were the case, then that would be nice and easy, and we'd have our job done. However, if the current is too big, electrical energy will be converted to heat energy and then lost while it's being transmitted over a large distance. So sometimes the electricity needs to be transferred over huge distances. It can be hundreds of miles, and if that's the case, then we can lose lots and lots of energy to heat because the current is quite high when it leaves the power station. So what we need to do is we need to introduce the step-up transformer here. So it leaves the power station, it goes to this place called this thing called a step-up transformer, which we'll look at shortly. It then is transmitted to wherever we need it to be, and then it goes to a step-down transformer before being received in our homes or our businesses. Now, in reality, there's actually probably more than one step-up transformer as it's leaving, and there are definitely more than one step-down transformer before it gets to your home. So it's stepped down gradually, and that's quite useful because different businesses can sometimes need different amounts of energy. So for instance, the power lines over the train tracks, they need a much higher voltage than we would use in our homes. In our homes we only use 230 volts, whereas above the trains they're looking for tens of thousands of volts that they're needing there. So we obviously want to make sure that everywhere is getting the voltage that it needs, the right voltage. Okay, so that's how we get our electricity from our home, or from our business to our home. How do these transformers work out then? Why don't we start off by asking the question, what is a transformer? Well, a transformer allows us to change the voltage and current in a circuit without losing any power, or in reality probably only losing a very, very little amount of power, or energy, of course, in the process. So let's have a look and see. So we start off with a coil of wire. Okay, so we've got a coil of wire here. Then we have a second coil of wire. So we'll call this one the primary coil, and this is where the energy is put into the system here. And we'll call this the secondary coil, and this is where our electrical energy is pulled out of the system. So let's move these closer together, okay? So just to remind us, that's our primary coil on the left and our secondary coil on the right. Now they're quite close to each other, so that's quite good to start off with. I do notice there's a slight gap between them there. They're not actually completely touching. The electricity isn't just conducted from one coil straight into another. But we also need another thing, which is this bit here. This is an iron core. Now the iron core just goes through the middle of these coils of wire and kind of almost kind of holds them together, I suppose. But it's another function which we're not going to talk too much about. This is basically a transformer. Now, what makes it a step-up transformer and what makes it a step-down transformer is the number of turns in each of these coils. So it's the number of turns in this coil or the number of turns in this coil. So let's pause the PowerPoint just for a wee second and let's have a look and see what we mean by turns. So what I've got here, I've just got just some wire. Okay, it's actually attached to a transformer already, but we'll pretend it's not. All a turn is, I'm just going to use my hand here to do this. A turn is just how many times the wire is coiled round, just how many times it is turned round. That's it, it's as simple as that. That's all we're talking about when we talk about turns. Dead easy. Those of you that have looked at electromagnets so far will have obviously kind of used these kind of turns, and you'll have kind of done something similar when you're trying to build your electromagnet with a nail or something. But that's all you do. You just get your wire and you just coil it round, and we call the number of times it's turned round here just the number of turns. It's as simple as that. Okay, so that's what we mean by turns. Okay, we'll be talking about turns quite a little bit as we go through this lesson. So let's go back to the slides. So if it's a step-up transformer, we would tend to have a different number of coils in here from in here, and likewise if it's a step-down transformer. But let's have a look at that in a little bit more detail on the next slide. So the transformer circuit symbol, this is important as well. This is a kind of a new circuit symbol that we should really be aware of. So I'm going to introduce this circuit symbol for you. Let me just move this out of the way. So this is our circuit symbol here in the middle of the screen. As simple as that. So what we've got here is we've got our primary coil and our secondary coil. And that could actually work the other way around depending on how you draw your circuit diagram. And in the middle here, of course, you have your iron core. That's what this line in the middle here represents. Okay, so let's move that over out the road just now and let's build ourselves a circuit. Okay, so we're going to build ourselves a circuit here. So I've got this wee device here. So this device here is an AC power supply. Now that's very important because a transformer won't work if you plug it into a DC power supply. So if you plug this into a DC power supply, your output voltage is always going to be zero. That's a nice simple solution. So you might have an input voltage with a DC power supply, but your output voltage, which you'll see over on the side in a little second, it would always be zero. So we always use an AC power supply with a transformer. So let's get rid of this circle here and we will bring back our transformer. So here's our transformer here. This is how it fits into our circuit. And then we introduce a second circuit here. And these are two separate circuits technically. So this one's hooked up to our AC power supply. That could be you plugging something into the wall, simple as that, hooking it up to this transformer, and then this transformer then hooks up to something else that you're looking to power. This could be your phone, for instance. Obviously, as you I'm sure hopefully are all aware by now, the voltage coming into our homes is 230 volts. So when we look at the voltage coming out of the wall, it's 230 volts. However, all USB devices need to use 5 volts, and that's a standard, and it's a standard that's internationally recognised because you want to be able to use a USB device anywhere in the world. You want to be able to take a USB device that you bought here in the UK, go to America, use it over there, go to maybe Japan or the Middle East or anywhere, and you want to be able to use that USB device. So USB devices always work at 5 volts. 230 volts is way too much, so we need to bring that down. And that's where a transformer would come in. We would bring that voltage down using a transformer down to 5 volts, and you could plug your mobile phone in here, for instance. Mobile phones tend to use USB chargers more often than not these days. So that would be one potential application for this here. One other thing we could do, and this is a useful thing to be able to do, and we'll be looking to do calculations based on this shortly. We could plug a voltmeter across these two terminals here, and we could calculate, or we could measure our output voltage from this secondary coil here, which we'll be going on to do just shortly. So the types of transformer, we've got two types of transformer. I'll give you a chance to read through these. I'll read them to you as well, just so that we are clear on this. Do feel free to pause the video at this point in time if you want to spend some time reading through these, or alternatively you can go away and you can look at the PowerPoint, which I will have put up separately in the Google Classroom as part of this kind of same material here. I'll try and kind of remove the videos and things like that to make it easy to view. So the step-up transformer basically steps the voltage in the circuit up. Simple as that. So if you have your power station, it's generating a voltage, you step that voltage up by putting it through the step-up transformer. Now, as a result of this, the current in the circuit has to drop. The reason for that is we need the energy to be the same. We can't create energy, we can't lose any energy by doing this, or we want to lose as little as possible by doing this. So what we do is we step that voltage right the way up to almost 500,000 volts. It's about 400,000 volts we're lifting this up to when we're leaving our power station. But as a result, the current comes down, and that actually allows the electrical power to stay constant. And as hopefully we're all aware at this point in time as well, remember, your electrical power is just the amount of energy you're using every second. Yeah, so that's quite useful, because we've now got a high voltage but a low current, and remember, it's that current that was causing us the problem. If the current was too high, we were going to be losing energy to heat. We brought that current right the way down, so we're going to lose much less energy to heat when we transport this over a long distance. Step down transformer, so once we get to the other side, as I've said, almost 500,000 volts. That's a huge voltage being transmitted along these electricity lines. We need to bring that down to something that's useful. It could be different for different businesses. Will require different amounts of energy. In our homes, we need 230 volts. So we would step it down in series. The step down transformer, as it sounds, just exactly the opposite of the step up transformer, brings that voltage back down to a level that is useful to us. So we're able to step that down to a usable voltage. Now, in the process, what we also do is we increase the current at the other side, which is useful as well, because it allows us to have the right amount of power when we need it in our homes. So this allows us to keep that power level constant. And in an ideal world, we would lose absolutely no energy on kind of transferring this, but we don't unfortunately live in an ideal world, so we will lose still a little bit of energy. But this allows us to minimise that amount of energy loss, or to keep it as low as possible, because we don't want to lose any energy if we can avoid it. So that's the two different types of transformer that you will be looking at, or that we will be using, or that we do use. So how do we go ahead and calculate the voltage then? So if we have, if we know about our transformer, how can we use that information to calculate our voltage? Well, we've got a nice equation here which we can use, and I say nice because it's not necessarily the most nice of equations. There's certainly nicer equations out there, but it's one that we need to know, one that we need to work with. So let's introduce this here. Now I've written this out in words for us here. The number of turns in the primary coil, remember the number of turns is just the number of times that wire has been turned round in that coil, okay? So I mean, it could be 10 times, it could be 100 times, it could be 1,000 times, it could be hundreds of thousands of times. It can vary depending on the transformer that you're using. So the number of turns in the secondary coil divided by the number of turns in the primary coil. So let's just look at that again. That's the number of turns in the secondary coil divided by the number of turns in the primary coil is equal to the voltage in the secondary coil. Remember, we put that voltmeter across, that was why we did that. Put that voltmeter across there, we could actually use that to measure the voltage in the secondary coil divided by the voltage in the primary coil. That seems, well, I'm going to say simple, maybe not, but it seems useful to me. So for those of you that are quite happy with working with equations, I've also got it here. This is how we would represent this just using letters. So the number of turns in the secondary coil would be represented by NS. The number of turns represented by the primary coil would be represented by NP. The number of turns, the voltage in the secondary coil is VS. And of course the voltage in the primary coil is VP. Now it's important at this point just to we highlight the fact the number of turns is just a number, so it says it here, it's a number. Because it's a number, it doesn't have any units. Voltage, of course, does have units. Hopefully we're all quite aware of that. Voltage is, of course, measured in volts. Okay, let's have a look at a little worked example just to have a look at how we would work with this type of equation, okay? As I said, I'm going to step you through this, so don't panic if you feel like you're not getting it, or if you're going, I'm never going to be able to rearrange that equation. For the examples I'm going to get you to have a go at, I've also got a help sheet which will just have all the equations, or the one equation, but rearranged into all the different variations that it can be in, so you can just lift out that equation that you need so that you're calculating just the thing you need. But we'll come back to that shortly. So worked example, let's have a look at this here. So a step-up transformer has 1,500 turns in the primary coil and 4,500 turns in the secondary coil. The transformer's primary coil is connected to an 11 volt AC power supply. What is the voltage across the secondary coil? Okay, at this point in time, what I would like to do is I'd like to just take a couple of minutes and highlight the important information here. So let's go through here. Let's read this again. So a step-up transformer has 1,500 turns. There we go, that's going to be useful. So I'm just going to scribble this over here nice and quickly. There we go, 1,500 turns in the primary coil and 4,500 turns. So again, that's useful there, 4,500, and it's quite annoying that that's over another line, but I'm going to just highlight this anyway because it's kind of important. I suppose it's almost a bit like the unit here. It's telling us what we're talking about. In the secondary coil, the transformer's primary coil is connected to an 11 volt AC power supply. Okay, so 11 volt AC power supply. I'm going to come back actually and highlight that in a wee second. What is the voltage across the secondary coil? So what is the voltage across the secondary coil? That's what we're looking to calculate. So there's 4 pieces of information that we need for our equation. Now, one other thing that I would like to just do just now is just to highlight this here. It's important checking to see that this is an AC power supply in the question, because if it's not, remember what I said earlier on in the lesson. Do bear that in mind. I'm not going to repeat it, but do bear that in mind. Okay, so let's have a look then and see how we solve this. So I'm going to take this information, I'm going to put it into my shopping list. That's always the first thing we do. I'm going to do it in a different slide because I want to give ourselves plenty of space to work here. So let's put that into our shopping list. So we've got the number of turns in the primary coil is equal to 1,500. We have the number of turns in the secondary coil is equal to 4,500. The voltage in the primary coil is 11 volts, and the voltage in the secondary coil is what we're looking to calculate. Now, if you prefer to work with the letters, the symbols for these, then I've included these here. But I'm going to be working with these just using the full written out versions, just to make it easier for everyone, make sure everyone can understand what we're doing here. So let's have a look. First step to get our first mark, or our next step to get our first mark, what we want to do is we want to write out an equation. It's as simple as that, and this is the easiest mark you can always get. If you copy out that equation, you get yourself a mark. Dead easy. So number of turns in the secondary coil divided by the number of turns in the primary coil is equal to the voltage across the secondary coil divided by the voltage across the primary coil. Nice and simple. Okay, so now what we want to do is we want to take these guys here and we want to plug these into the right place here. So this is easy. We just look for number of turns in the primary coil, which was down here, and we change that to 1500. I'll do that here. We look for number of turns in the secondary coil, which is there. That's 4500, so that one goes on the top, and that equals voltage across the secondary coil. Well, we've got a question mark here, so we just leave that as it is. And then we've got voltage across the primary coil. That was 11 volts, and it's on the bottom there. So there we go. Simple as that. That gets you another mark. Remember, that's you at 66%. All you've done is you've taken the information that's given to you in the question and managed to get it into the right places. And that's why we like to write these. That's why I like to get you to write these things out the way that I do. Okay, so let's rearrange this, and I'm going to do this using the rearrangement. Those of you that want to kind of follow through and kind of try the rearrangement, feel free to follow this. If you are completely lost at the end of it, don't worry, as I say, you get the equations in the form you need them anyway. So I want to get this here on one side of the equation by itself. At the moment it's divided by 11, so we've got voltage across the secondary coil divided by 11. If I want to get rid of this divided by 11, I need to bring this divided by 11 over to the other side, but I need to change the sign when I do that, so the opposite of a divide is a multiply, so you're just going to change that sign to the opposite sign. So we bring it across and it becomes 4500 divided by 1500 times 11. Simple as that. And then we've got voltage across the secondary coil. We have that in one side of the equation, and that's what we're looking to do. So now we can go ahead, we can plug those numbers into our calculator. So we do 4500 divided by 1500, then we multiply that by 11, and of course we come out with 33 volts. So that is the voltage across the secondary coil. Yeah, at this point, what I would do personally is I would change this around, because I just prefer the words to kind of be on this side. So the voltage across the secondary coil equals 33 volts. That's not something you have to do, but you would get your mark here as well. So let's just have a look at those marks. So let's just go back to the start here, have a look and see where we're getting our marks. So our first mark, as we said, we get from writing down this equation here. That gets you your first mark. That's 33% of the marks that you're getting for this equation. You get your next mark for substituting in your numbers, so that's this step here. You're going to get another 33%, which actually takes you up to 67%. It's 33.3333, it's 33 and a third percent. So, so it's 66 and 2/3 of a mark, so that's 67. Remember, that's a B at National 5, if you manage to get that far in the rearrangement of an equation. Then finally we do our rearrangement. We don't get a mark for that, so you don't technically need to write that step down, but if you feel you need to in order to get to the final step, then it's worthwhile doing. Your final mark, of course, comes in for your correct answer, including your units. Okay, now you get it for either of these. I've kind of put this between these two lines. You don't need to rearrange this, you don't need to swap this over like I've done here. That's just my preference. That's how I like to work this, and that's how I like to display my work. But that's not necessary, and if that's going to confuse you, just don't bother doing it. Leave it the way it was. Okay, so hopefully that's nice and clear. Now what I'd like for you to do is to go away and have a go at some problems by yourself. So I've written a worksheet called Transformer Questions. It's included with this material, with this video here, so you should be able to find that nice and easily. So have a look at those questions, have a go at them. Hopefully it should be easy enough. There are different things that you're asked to do. So sometimes you're asked to calculate the voltage in the secondary coil, as we've just done there. Sometimes you're asked to calculate the voltage in the primary coil. Sometimes you're asked to calculate the number of turns in the primary or secondary coil. There's some questions. I'll do all of those. See how you get on with them. Try your best. On the Google Classroom, and beside these, there's also another sheet called Transformer Equations. I've kept that as a separate sheet just to make it nice and easy for you. You can have both of them open at once if that's useful for you. And it has basically all of the equations that you might need, or this equation rearranged into all of the different forms that you might need to answer any of the questions that are in the question sheet. Check your answers, so I'll put up answers as well. Do check your answers against the answer document. Make sure you're getting them right. If you're not getting them right, try and see if you can figure out where you've gone wrong. If you can't figure out where you've gone wrong, ask the question. Pop a comment on here down below in the comments, or in the or you can send a private comment, send an email via the Google Classroom. Any method is absolutely acceptable. Ask for help if you need it. As I say, Mr. Warnock, Mr. Scott and myself are all here to help should you need it. In the meantime, I'm going to leave you at that. What we'll do is we're going to put up the success criteria again here. I want you to check off the success criteria. So, do you understand what the challenge was? What was the issue, the big issue that we had trying to get electricity from the Pooper River we generated it to our home? What was the problem there? How did we solve that problem? What was the use of the transformer? What did the transformer do? The different types of transformer, and of course, equally as important, have you managed to answer those questions correctly? Okay, if you can answer all of those, you can give yourself a big tick for each of those. Very happy at that. What I'll probably do is I will probably ask you maybe to submit your answer to one of the problems that I've put online. I'll ask you to do that either at the end of this week or at the start of next week, so that we can see how you get on. In the meantime, you guys keep yourself safe. Hopefully we're going to get to see each other soon, and I'll see you later.